Get started. Welcome to Robotics 311. Today we will review our torque conversions. We're going to discuss some of the kinematic conversions that we learned originally. I'm going to kind of show you the background of how those formulas were obtained. And then we're going to break. I'm going to try to break just before 1, maybe 15 till, to let those who need to finish up the lab go back over this with FRB and finish it. Couple announcements. Homework 3 is posted. It's due on October 20th. We're going to upload the quizzes, the quiz solutions, and the homework solutions, so you will get to that soon, I think. There's no class next Tuesday on the 18th. It's like fall break of some kind, so we don't have class, so don't come. And then the midterm is on November 8th. One thing that I noticed, I wanted to share this with more people, but only about half the class is here. One thing I noticed is that like a lot of people, you guys heard on last lecture, you guys I thought were tracking the force conversions like really well, and that was awesome. That made me think like this is going well. You're kind of understanding how the planar model fits and applies torques to the real system. And then lab, I thought it felt like I was more concerned that people like weren't tracking the hands-on stuff well. So some people I think are very proficient with hands-on work, connecting with the Raspberry Pi, interfacing with Python and SSH. But some people were like very unfamiliar with it still, which is fine. That's totally normal, but you kind of need to be proficient in that for this class. So if you are not proficient or if you feel uncomfortable, you need to go back through and redo the lab we did in the beginning where we connected to that Raspberry Pi. You can look at the resources that were uploaded. There's lots of Python resources and information about Raspberry Pis and using Python. So like that stuff, if you don't have that kind of thing down, that's what we're going to spend the labs really like teaching that over and over, which prevents us from doing the things we need to do, which is going to be getting into control and actually making the ballbot do what we want. So the hands-on skills of interfacing and connecting and coding in Python, you just kind of have to know that stuff. And if you don't, it's going to be a challenge. So that's unusual because this class requires hands-on knowledge in addition to theoretical content knowledge like we're going over in class. So you have to take time to learn that if you don't know it, just like you would for class material. Just you won't be reading a textbook or looking over lecture slides. You'll be getting out your computer, connecting to the Raspberry Pi is a kind of a different style of work, but it's really, really important. So please share this with your classmates. Maybe I'll post an announcement, but you kind of gotta know that stuff well because we're just gonna build on it. If we don't know, we can't really build on it. Okay. So let's just go back through the full planar model real fast. So this I thought you guys were tracking. We're taking this three-dimensional ballbot. We're going to split it into 2 planar models. We're going to handle each one of those planes separately. And that's what's going to end up happening. That's how we're going to control it in 3 dimensions. It takes this 3-dimensional problem, puts it into 2 2-dimensional problems. That's much easier and maybe even more intuitive. It's easier to think about what are the corrective torques that need to be applied in a planar model rather than a 3D model. So we're going to end up analyzing it in 2 dimensions, computing everything we need to compute, sending that information to the motors, which then we convert it back into 3 dimensions. And that's what we did with that MATLAB code. We created the initial program to take the 2-dimensional torques and convert them to the 3-dimensional torques. Then in lab, you're doing that in Python. So you're creating a Python file that does that. That will become a function that you use because part of this will require that every single control cycle. So we talked about this. I think you guys are tracking it, which was awesome. This was kind of how we talked about converting torques. We needed both the forces at the virtual and real wheel locations and their radii. We looked through the geometry, determined their radii, and then determined how to calculate the forces. We did note that this is a little bit, so there are some sort of strange conventions in the math that we're using from this dissertation. One is that the direction of the forces implied by these subscripts is not the actual vector direction. So that I want to make sure you guys note. There's also a discrepancy in their z-axis formation. They have a z-axis issue where they're not using the right-hand rule. And we're going to try to keep the math in this class the same. So following that dissertation, but then there is this correction that we will do in software that you guys will never see. But they did some inconsistency things. So if you look at this and you think to yourself, wait a second, that's the axis is supposed to be going down instead of up. That's true. But since they've defined everything this way, we're going to continue with it this way. So I think at least the summary for that is you don't need to worry about it. We'll take care of it. But there is an issue with the way they selected their axes. These are like actual torque conversions. In the next slide, we show the torque conversions for the more general system that includes alpha and beta. This includes those expressions, but solved with our beta value. And then these are supposed to be pluses. Change that. They were minuses last time. Yeah.
What's the beta value again? I can't remember.
Beta value is the orientation of the 3 wheels into this XY plane.
Okay.
And so when we said we oriented the y-axis to be motor 1, that was beta. That was sort of a parameter that we chose to make it easier. It's just easier if they're aligned like this. So this was our expressions from the dissertation. They're maybe a little more general, because you guys want to see those. Okay, and now what we want to talk about is a similar conversion for the kinematics. So how do we take ball motion and convert that to wheel motion, given that the system may not be perfectly upright at all times? And you saw this equation. The result of this analysis is an equation that you saw when we were doing the planar modeling in the beginning, in the speccing process. So now we're going to go through that for a few slides, show you where that expression came from, and then I'm hoping to transition to sensing and data acquisition after that. Do that for a little bit and then stop just before 1. Okay. So we can now describe torque from the wheels to the full planar model. So we can go from X and Y components to motor torques. V1, V2, and T3. Can we develop a similar analysis for velocity? Similar, it won't be quite the same because we're not going to do these velocity transformations in your actual software. You will have to end up doing the kinematics potentially if we want to convert motor angle to ballbot angle, but we'll get to that. So this is a similar analysis of understanding how motion of a wheel translates to motion of the ball. Okay, the real wheels and the virtual wheels, they're the same size, so they're the same diameter. These virtual wheels are the same size as our actual wheels. Do they have the same velocity? Remember, so these are our virtual wheels. Those wheels have the same velocity as our real wheels. No, why not? Yeah.
Or aren't they acting in different directions?
They're acting in different directions, they're in different locations, and they split the motion across the 2 planes, whereas each wheel, as the virtual wheels, only do 1 plane at a time. So we'll say no. Orientation of the wheel affects its velocity. After we do sensing, data acquisition, and mechatronics, I'll tell you about the wheels. I haven't gotten to these wheels yet. But something to know is the real wheels only spin with the component of velocity. With the component of linear velocity. Perpendicular to the wheel axis. So we have our real wheels are spinning on the circumference of this ball, and that ball is rotating, but it's not necessarily rotating in such a way that those that the motion of the wheel contact points on the ball is perfectly along the direction of its velocity. So it means these wheels sort of slip. So they allow rotation, they're omni wheels, they're going to allow rotation in the other direction, but that doesn't happen through motion of the wheel axis, it happens through spinning of the rollers that are around the wheel. So the only motion that the wheel axis will provide is the motion of the component velocity that's in that direction. Does that make sense? If I have a ball here and a wheel here, the only way that I can get the wheel to rotate with the tangential velocity of the point here is if it's rotating along that direction. As soon as it starts to rotate in any other direction, the velocity the wheel angular velocity will take on the component of velocity vector in that plane, and then the rollers will allow rotation in the other plane. And we wouldn't sense that or know that it's happening, but it allows for that. So the only component of velocity that we're looking at is in the tangential, it's the part of the velocity that's tangential to the axis that's perpendicular to the wheel axis. Okay, so now what I want to do is kind of dive into this diagram. We want to look at points A, B, and C. What is V, A, Y? Now I'm going to talk about velocity in the XY components, or YZ components. What is the velocity here?
0.
0. V, A, Z, 0. Okay, what is V, B, Y? So I want to know the component velocity of point B in this direction. The ball is rolling. So what are some things that are going to describe that velocity, the linear velocity of that point? How fast it's rolling, which would be yk dot. Plus, what other terms are going to be in here? And what variables? We're looking at the linear velocity of point B in the y direction. Yeah.
Also the angular velocity on the radius.
Yeah, so we're going to do phi dot rk cosine of theta x. Okay, so this is our description of the linear component of velocity of point B. How about the z component? So we're not going to have any yk, so that's going to be 0. So we have our x and y components, the velocity of this point, yeah.
Would the sines and cosines be swapped here? Because if you're looking at your angle being
Like the angle from like the center, like that. Like, wouldn't it be sine if theta? I might be looking at the wrong theta then, but is it the top one?
It's the top one, it's this theta.
Right, so
Yeah, I think it should be
if you're
sine.
looking at like the horizontal component of that,
Can you check that? I think it should be sine. I agree. So we'll come back to this. So let me just keep working this thing, working it out, but I'm with you that I think those should be swapped. So that could either be that I entered it in wrong, or it could be that there's an issue with the way it's defined. I'm going to keep going though, and we're going to do velocity of point C. What we're going to end up doing is describing the linear velocities of these points. Then we can do something special because of the no-slip condition between the wheel and the ball. So we'll be able to equate the velocities at points B and C. That's where this is going. So they start to get a little more complicated. Now we have to handle not just the rotation of this, but also the rotation of that. These are also like sine and cosine. So they follow that, so it makes me think I didn't enter it in wrong. Okay, so this is the expression for the y component of velocity at point C and the z component of velocity at point C. And all we're doing is using our roller physics to understand what are those velocities. And then the trick is we can equate them, which comes from the no slip condition. So we can say VBY equals VCY and VBZ VCZ. Now I'm just going to write that out. Vy equals that's our y components set equal to each other. What's convenient about this is a ton of terms drop out. Cancels. Cancels. So we can do the same thing for VZ. Same thing for Z, and again, terms drop out. Kill the sign. So we end up with this expression. Okay, so we're close. Now we're like getting close to an expression that makes sense and is not too hard to look at. Yeah.
On the second line of the third to last term, with the subscript x, what is the letter?
This?
Yeah.
Psi.
It's supposed to be psi dot or just psi?
Psi dot. Yeah. Okay, so we're close to having an expression that makes sense, and it's relatively tractable. We end up with our 2 degrees of freedom equation. I'm going to finish this explanation and then we're done with this. This expression tells us how all of these motion variables are related. We can rearrange it and solve for psi dot x, which is rk over rw, p dot x minus rk plus rw over rw theta dot x. We can simplify that one more time to this expression. Psi dot x is rk over rw v dot x minus theta dot x minus theta dot x. Okay, so this is our virtual wheel velocity. That's our ball velocity. That's our body velocity.
So you say body velocity, is that the speed at which it would be moving like on the XY grid, or is that like how the small ball is moving in relation to the big ball?
Yeah, this is the body, it's pulling this, it's this angle.
Okay.
What of these in your system, what of these do you know, and what of these do you not know in this expression? Do you know the wheel angular velocity? / can you calculate it? Yes. So that you can measure. We're gonna talk about encoders, we can measure that from the motor. So that we know. Do you know the ball angular velocity? No, we don't know that. Do we know the body velocity? Yes, that we do know. We measure it from the IMU, which we will also talk about in the chassis. So this equation can be used to determine the ball angular velocity. We still need to convert from wheel velocity from virtual wheel to real wheel. Yeah.
Why are the velocity
Of the ball and the wheel, or the angular velocity of the ball and the wheel the same? They're like connected and rolling without slipping.
Because of this. Imagine this ball is stationary and all that thing's doing is rolling around it. Like because it's rotating over top of the ball.
Oh, but isn't it like
Staying the same. I guess like for this particular like planar model, like it isn't, but
oh, it is, I did not know that.
Would we want to use this equation if we know the velocity that we want for our ball and then find the wheel velocity, or would we use this equation if we know our velocity and our body velocity to figure out the ball velocity that we're moving at?
It's the latter.
Okay.
But this, right now, we haven't been using a velocity-based controller. So it's unlikely, or it's at least like up until the last week, we weren't really planning on using this equation, like in the actual control. Something that I want you guys to know and be exposed to, how the motions of these different angles relate to the rotation of the different components. But it is possible that we change the control and then use it, in which case like, you'll hear about it more later. Yeah,
Previous slide was right. The sine theta cos theta
yeah,
is right.
okay. And then, all right,
So it's tangential velocity, right?
yep,
So this angle is theta, it's tangential velocity. So if you resolve components, the vertical component will be sine theta, v sine theta.
okay,
And this is theta.
yeah.
The initial theta you were looking at, if you're looking at that as a horizontal component, would be for yk. But when you actually resolve the tangential velocity at point B, you do a lot of flipping of theta and theta or 90 minus theta, and it ends up actually being that it is cosine.
Got it. That makes sense. Okay. And also, like, there are most of the things we find in this dissertation, we're like, we don't think that's right. We work through it, and it's right. So that's like only a couple of times has that been not true, but we've probably done that 10 times, and always, all but one or two, it's actually right. Yeah.
For certain problems on the homework, we had to do math like this. Like I think the last problem on the homework is something similar to this. Are we assuming RW, alpha, all those values are what we like originally talked about for our ballbot?
Yes. If I ever want you to use other values for that, I'll make sure that's very clear. Cool. Okay. I want to take for the next 15 minutes, I want to talk to you about sampling. So this is what we're going to, for now, based on our understanding of the way we're going to solve control, this is as far as we'll go. If we end up using velocity back, then you'll see this more again. But I suspect most of what you'll see when we get to control is about the torque conversion. But this is all we're going to do for kinematics for now, is to give you guys a working knowledge of how the different variables relate to each other. Now I want to move to acquisition sensing and mechatronics, which we will then, after that, go to control. And that's kind of the end of the class, I guess. Control is the last thing we'll do, and we'll do it for a couple of weeks or more. Okay. So this is about sensing and data acquisition. Key things for robotics, but also key for just general engineering knowledge. And some of you, I'm hoping some of you have seen this before. Like a key aspect of any robotic system is going to be sensing its state or the environment. It's how we understand what to tell these robots to do. For the ball angle, what do we want to know? There's two variables we probably have access to and want to know. We just said them. What are they for the ballbot? Yeah, we'll say like ball wheel rotation. Oops. What was the other one? Lean angle. Yeah. Wheel rotation and lean angle. In the coming slides, we're going to talk about how to use sensors for acquisition. There are two types of data acquisition systems. Anybody know one of them? If I give you one, can you give me the other? One of them is digital. Analog, yes. What is analog? What is analog signal acquisition? What does that mean? Yeah, we're recording a continuous value. Continuous voltage sampled and interpreted. How about for digital systems? How's that work? What? On and off? True, but that's not what we mean here. In an analog sense, you guys seem to have seen the analog part. You're sampling a data acquisition system, you're getting values back. In a digital system, it's the same, except you're not sampling an A to D card, you're requesting a digital value from a sensor, and it responds with that value. So digitals is information sent over a communication protocol or communication bus in the form of ones and zeros. That's why it's digital. Not, I mean, on, off, yes, but it's digital communication. Okay. Our ballbot only uses digital or analog? Digital. Our ballbot only uses digital sensors. But we're going to quickly review analog sensing because I think it's easier to track the key parts in the analog world, and those key parts are the same in the digital world. So previously, like analog systems were by far, there were no digital systems. Everything was sampling analog voltages. That's slowly been changing over probably the last like decade now, or maybe 5 years especially. Now most sensors you buy are digital, which just makes everyone's life easier in one sense and maybe harder in another. But let's start with talking about analog systems. Okay, so this makes up the common pipeline for data acquisition. There's going to be a physical process or something, so there's a ball bot, it's motion, it's lean angle. There'll be some sort of sensor transducer that converts that physical process into a voltage. You might condition that signal with filtering or some other types of conditioning. Then it will be sampled and converted. So then it'll be sampled by something called an analog to digital converter or A to D card. And then that's sent, those values are sent digitally to a computer. Accomplished using a data acquisition system. That's kind of the terminology. There's three key attributes of a data acquisition system. Anybody know one of them? Who's collected data from an analog system before? Okay, not a ton. All right. So there are three things that you when you did that you saw or you imposed. One of them is real straightforward, the other two are more nuanced. Sample rate. Sample rate is the most important factor. So how fast you sample it. 3 key attributes of an analog data acquisition system: sample rate, which is described in hertz. So that's how many times you're using your AD card to sample that analog voltage. So it's going to be, is it 50 times a second? Is it once a second? 1,000 times a second? So that's how many times you're interrogating this analog to digital system, and it's responding with its values. The next sample rate, how fast the next one is bits. When you guys were working with your A to D, analog A to D systems, you probably interfaced or noticed that your A to D system is defined by a number of bits. A 16-bit A to D system, an 18-bit A to D system, 8-bit or 10-bit. So we describe by a number of bits. That number of bits tells us how many bins there are to represent the voltage. So if we sample something, it's going to convert it to an integer, digital value, could come into a computer. And so how many values can that take on? Can it take on, if it's 16-bit, you have 65, 535 options. If it's 8-bit, you only have 255 options. So the number of bits tells you how many bins do we get to break the voltage up into. So the last one is input range, which is going to be in volts. So this is the total range of that can be sampled by your A to D system. Let's say if we think about input range and bits, let's think of how small of a change can we actually measure, which I'll say is a delta V over bit. So this is how many volts per bit. If we have a large number of bits in our A to D system, we can have a large number of bins. This is going to be a small number. If we have a small number of bins, it's going to be a large number. The way we calculate this is our voltage range divided by 2 to the bits minus 1. This 2 to the bits minus 1, that's the total number of bins you have. That's 65,535 for 16. So if you do 2 to the 16 minus 1, it's 65,535. If you do 2 to the 8 minus 1, it's going to be 255. So this tells us how many bins there are. A higher number of bins, a number of bits gives us more resolution in our data acquisition system. Our voltage range is the total range that the input and output can take, or the input can take. So it's usually minus 10 to 10 or minus 5 to 5 or something like that. Yeah.
Why the -1?
Because 0 is 0. 0 bits is really the first. 0 means no signal. So that's that takes one of your bins. Yeah.
So if you have like a voltage range of
-10 to 10, would you then like normalize that across the number of bins, or like?
No, so if you had minus 10 to 10, V range would be 20. You have 20 total, you have 20 volts.
but then
Over like the amount of bits, like, so then you can just store like each
I guess the amount of
things or small changes you could store would then just be divided by the, okay, I don't know, I was just like thinking about like,
Let me keep going, I think that'll clarify. So this is really telling you the smallest change you can measure by one bit flipping, 1 bit change. But let's think about like, how do we actually calculate the voltage? So to calculate voltage, when you sample an A to D system, what will it return? So let's say you're in MATLAB or in Python, you're getting a voltage from your you're getting a value from your A to D system. What will that number? What kind of number is that? Can it be a floating point number, it'll be an integer. So this will return an integer. An integer, I want to say number of bits, but I don't want that to get confusing. It is a number of bits, but I don't want that to get confusing with the number of bits of your A to D card. These bits need to be converted back to voltage. We're going to do an example in a second. So you read something, you'll say you have an Arduino, you're reading your sensor, you get a bit value of 200. Is that on the low end? An Arduino samples at 8 bits. Is that on the low end or high end of its voltage that it's measuring? On the higher end. So if it's reading 200, its maximum value is 255, you would know that it's on the higher end of voltage, but we're going to figure out exactly how to calculate it. So once you get your integer number from your A to D card, you have to convert that back into volts, and then you have to convert it back into the units of the original system that was measured. So there's two conversions that happen. The first conversion we're about to discuss. The second conversion depends on the sensor you're using. Okay, so after converting to volts, it needs to be converted to the original units of the sensor or process being measured. So it could be meters or amps, something like this. That's accomplished by using the sensors, what's called sensitivity or calibration curve. Those are always in the data sheets. But what I want to tell you now is like, how do you go from a sampled number of integers back to volts? It's this equation. So our sensor voltage, which is what we would end up using, we go back to the original, let me finish that, the original units, equals Vmin plus V times V range over 2 to the bits minus 1. Where this, that's your integer. Red for your A to D system. Okay? This is an example of an analog to digital converter. Just a National Instruments really common brand, plugs into a USB port. So this is sampling an analog voltage, transferring it digitally to your computer. You can also buy A to D cards that are like from SparkFun, that would be little tiny ICs. So they take on many different forms. This is just an example of one. Here is my question for you. We're working on something, and we're recording a value from our A to D system. It's a 16-bit system, which is what that would be. We get a value of 11564. What is that voltage? I want you to convert it. Yeah. Right here. Right here. Or do you know the voltage? Everyone calculate the voltage. So I know that you guys know how to do this in our tracking week.
What's the max capacity of 16-bit integer again, or 16-bit number?
What is that number?
Yeah.
65535. Who's done? Who's got a number? Who got minus 6.47 volts? Yay, all right, good job, guys. So that, you got that by saying minus 10 plus 11564 times 20 over 65535 equals minus 6.47 volts. Okay, so now we'd have a sensor that's reading minus 6.47 volts. That was this process. We just converted it from a bit reading that we got from our analog to digital converter, which had an integer value of 11564, and we converted that back to the voltage that the sensor was actually reading. Now, let's say that was, a load cell, then we would have to say, okay, we need to know how to convert volts back to newtons. So then we'd look up in the data sheet, find its sensitivity, or the conversion between volts and newtons, and then apply that and go back into newtons. Okay. Signals are sampled periodically. They have a frequency governed by the sample rate. When you sample something, we aren't sampling it perfectly, because we can only take on values. So this is an example of a function over time where gray is a signal, red is the sampled values, and then the dashed lines indicate the bit level resolution. So that's going to be our input range divided by 2 to the bits minus 1. So we can only take on those values, only the integer values that would make up the dashed lines here. So when we sample the signal, we're not going to sample it perfectly. We're going to get some differences there. That difference is called quantization. This causes some quantization of the analog signal. Which will have more quantization, A to D card with a low number of bits or a high number of bits? Low. A low number of bits will have much more quantization because we have a smaller number of bins to kind of put those voltages into. The most important factor that governs your analog to digital and data acquisition system is the sample rate. And I want to tell you what that affects. Does anybody know why sample rate is so important for measuring signals?
How fast your numbers updated. So like
That's-
how accurate your data is, when you're reading it in.
That's true. The delay is minimal, is that what you're saying? That is true, but there's a different thing that's, I'd say, a bigger deal.
Yeah, aliasing if you're not signaling fast enough.
Yeah,
The signal you see is not the actual signal.
that is correct. So I would say it governs the frequency content, which is aliasing is a part of. The frequency content of what can be measured. In robotics, we're often sampling things that have high frequency content. So fast motions, impacts, those kinds of things, which require a really fast sample rate. Higher sample rates can sense higher frequencies. This is the key concept here. There's something called the Nyquist criterion. The Nyquist criterion says the maximum frequency you can measure is 1/2 the sample rate. So if we have a sine wave, the maximum sine wave that we can measure, if we're sampling at 100 hertz, the maximum frequency we can see is 50 hertz. So that is a really important number, is what is the maximum frequency that you can see. And a lot of times that comes into play for control and for your original goals of the robot. For sort of prototypey robots like we're doing in this class, this isn't as big of a deal. But certainly in robotics and mechatronics in general, it's really, really important. I'm actually not going to talk about aliasing just because I didn't want to go any further into this. But aliasing, what happens for aliasing, let's say we're sampling at 100 hertz. We have a 50 hertz Nyquist frequency, so we're not going to be able to read anything faster than that. And we know there's a 200 hertz sine wave in that signal. What we would see, so that's much faster than we can see. So rather than seeing that sine wave, we'll see a downsampled version of that sine wave, which is also a sine wave. Now what happens is something that existed at a much higher frequency, once it gets sampled, looks like a lower frequency. And so in order to prevent that, a lot of times people would add a hardware filter to block out any frequencies above the Nyquist criterion. That is a level of detail that I think I can speak to you, but wouldn't require you to know. The highest frequency that can be measured is half the sample rate. So this is, you have to set that carefully when building a robotic system. So you have to know something about your frequency content of what you're measuring. In the ballbot, most things are pretty low frequency. It's rolling and moving. There might be some impacts, but the signals that are happening are pretty low frequency. So we don't have to worry about this a ton. And our system will run at 200 hertz, which is slow for update rates, but fast enough to capture the frequency content that we need, likely also fast enough to have the control behavior that we need. Okay, so next was digital. Actually, I'm just gonna, no, I'll save this. Okay, so I'm gonna stop here.